Hello everyone and welcome to this hands-on session on calculation and interpretation of non-parametric tests. In the previous session, we have discussed the different non-parametric tests like chi-square, Mann-Whitney U, Wilcoxon Signed-Rank test, Kruskal-Wallis H test, Friedman test and Spearman's correlation test. In this session, we will see how to calculate them using data. By the end of this session, you will be able to compute the non-parametric hypothesis tests using SPSS and interpret the results in context of your research. Let us begin with the chi-square test, which is a test of independence. For this, we will be using the sample dataset in SPSS survival.sav, which has data of patients of different age group and gender, whether or not they are smokers, their history of blood pressure, diabetes, cholesterol, angina, the number of episodes of myocardial infarction or heart attack they had, and many other variables which are defined in the variable view. The scale of the data is also mentioned here. Let's say that we want to find if there's any relation between smokers and their history of angina. Over here. The null hypothesis here is that angina is independent of whether the patient is a smoker, and the alternative hypothesis states that angina is dependent on whether the patient is a smoker. Note here that both variables are categorical or nominal, that is, they have no particular order and it is labeled as such in the variable view. To perform the chi-square test, we go to Analyze, Descriptive Statistics, Cross tabs and select Smoker in the rows and History of angina in the columns. It doesn't actually matter which you put in which. Now go to Statistics and check the boxes which says chi-square. Note that the chi-square statistics only tells if there is an association or not, but it doesn't say anything about the strength of the association. For that, we need to see the phi and Kramer V values. Phi, if the variables have two categories only, like a yes and no, and Kramer's V if one of the variables has more than two categories. So we'll tick the box for the phi and Kramer's V and click Continue. Go to cells and check the expected outputs count. Click Continue and then OK. Let us look at the output and see how to interpret it. The case processing summary tells us that there are 2421 number of data points and there are no missing values. In the cross tabulation table, we see the actual and expected counts. The actual count tells the number of data points in the dataset, whereas the expected count tells that if there was no interaction between the variables, what the count would be. Below the chi-square table, we also see that 0% of the expected count value is less than 5. This should always be less than 20 for the test to be considered valid. This is an assumption of the chi-square test. Also, none of the expected cell counts should be less than 5. If it is, then the Fisher's exact test should be performed. For this case, since all assumptions are met, let us look at the chi-square test value. It is 90.343 with an asymptotic significance of 0, which is less than 0.05, and hence it is significant. Hence, we can conclude reject the null hypothesis, which indicates that angina is dependent on whether the patient is a smoker. Now, let us look at the phi measures. It is 0.193. As per the textbook on research methodology by Deepak Chawla and Nina Sodhi, a phi value of less than 0.2 indicates that the strength of the relationship is negligible. Between 0.2 to 0.4, the strength is weak. Between 0.4 to 0.8, it is moderate, and greater than 0.8 indicates that the strength of the relationship is strong. Since here the phi value is almost equal to 0.2, we can conclude that the strength of the relationship between occurrence of angina and smoking is weak. Let us now go on to the Mann-Whitney U test, which is used to compare the means of two groups and is the non-parametric equivalent of the independent sample t-test. Just to recap, the assumptions of this test are: dependent variable should be continuous, independent variable should be of two categories, the observations are independent, and observations are not normally distributed but should follow the same shape. Let us take the telco.sav dataset from SPSS sample datasets for this. For the dependent variable, we will choose the household income, which is a continuous variable. And for the independent variable, we will choose retire, which indicates whether the person is retired or not. This is a categorical variable with 0 indicating not retired and 1 indicating retired. The observations are independent, and to check whether they follow the assumption of being not normal, we will do some basic tests. For that, we first split the file according to the categorical variable, that is retired or not retired, by going to Data, Split File, click on Compare Groups and select Retire as the variable the groups are based on, and click OK. After that, go to Analyze, Descriptive Statistics, Frequencies, and move your dependent variable, in this case the household income, in the variables box. Click on Statistics and choose some basic statistics like mean, median, skewness and kurtosis to be displayed. Click Continue. Go to Charts and select Histograms and click Continue. Untick the display frequencies tables because we don't really need that, and click OK. Over here you see that the entire statistics has been divided into no and yes based on retired or not retired. From the skewness values as well as from the histograms, we see that the data is not normally distributed and heavily right skewed. Now we go on to do the Mann-Whitney U test. For this, we have to first ungroup the data. So go to Data, Split File, and ungroup the data by clicking on the first button here which says Analyze All Data. OK. Now to perform the Mann-Whitney U test, go to Analyze, Non-Parametric Tests, Legacy Dialogues, Two Independent Samples. In the dialog box, we choose Household Income in the variable list and Retired as the grouping variable, and define the groups as 0 and 1. And click Continue. By default, you will see that the Mann-Whitney U checkbox is ticked here, so just click OK. The output shows the Mann-Whitney U value as 10,999 with a significance of less than 0.05 or even less than 0.01, which means that we can reject the null hypothesis, which here is stated as there is no difference in the distribution of household income across categories of retired. If you perform the Mann-Whitney U test on the same dataset with gender as the independent categorical variable, you will find the results to be not significant, and then we will fail to reject the null hypothesis, which is there is no difference in the distribution of household income across categories of gender. You can also do this test in another way. Go to Analyze. So first we go back to our data window, then go to Analyze, Non-Parametric Tests, and click on Independent Samples. Choose Household Income in thousands in the test field and Retired as the grouping variable. Go to Settings and you will see automatically choose the tests based on the data already selected. Choose Customize Tests and choose the Mann-Whitney U test if you want to, but here I will leave it at automatically choose test based on data and click on Run. The results table shows that the software has chosen to do a Mann-Whitney U test which is significant at a level of 0.05, and it also states the null hypothesis over here and the decision taken based on the analysis, that is to reject the null hypothesis. Let us quickly do the same analysis for marital status. So we go back to this and go to Analyze, Non-Parametric Tests, Independent Samples, and here in the fields, instead of retired, we choose marital status, and everything else is the same. So we say click on run, and you see here the non-parametric test result, and the results show that retain the null hypothesis or fail to reject the null hypothesis. Next, we go on to the Wilcoxon Signed-Rank test, which is the non-parametric alternative to the paired sample t-test. For this, we choose the diet study sample dataset in SPSS, which gives weights and triglyceride levels of individuals before and after a diet program. The simple way is to go to Analyze, Non-Parametric Tests, Related Samples, and add the variables weight and final weight in the test fields. In the Settings tab, keep the Automatically Choose Tests based on data and click Run. The output shows that the software has chosen the Wilcoxon Signed-Rank test based on the data, and it is significant. SPSS also provides the null hypothesis statement, which is the median of differences between weights and final weight equals 0, and the decision, which is reject the null hypothesis. The same can also be done by going to Analyze, Non-Parametric Tests, Legacy Dialogues, and choosing two related samples. Choose the test pairs as weight and final weight. And note that the Wilcoxon Signed-Rank test is chosen here by default. Click OK. The test statistics here show that the test is significant, and hence the decision is to reject the null hypothesis. It also provides some additional information in the ranks table. If you remember, our data set had data from 16 individuals, and the ranks table here shows that the final weight is ranked lower than the initial weight for all 16 participants, and none are greater than or equal to the initial weights. Moving on to the Kruskal-Wallis H test, which compares 3 or more independent groups. Let us look again at the stroke survival sample data set. This time we want to test the null hypothesis. The distribution to time to first event post attack is the same across categories of blood pressure. We see in the data set that blood pressure is split into 3 categories. Zero for hypotension or low blood pressure, 1 for normal, and 2 for hypertension or high blood pressure. The time to first event post attack, defined as the variable time 1, is a scale variable. To perform the Kruskal-Wallis H test, we go to Analyze, Non-Parametric Tests, Independent Samples. In the objective, click on Customize Analysis, go to Fields, select Time to First Event Post Attack, and move it to the test field, and blood pressure to the groups field. Go to Settings, choose Customize Tests and click Kruskal-Wallis one-way ANOVA K-samples with all pairwise comparisons and click Run. The significance here is 0.01, which is less than 0.05, and hence the decision is to reject the null hypothesis. Let us double click on the hypothesis test summary to see the post hoc test and determine between which groups are the difference actually significant. Go to View at the bottom of the screen and choose Pairwise Comparisons. Here you see that the difference is significant between the groups normal and hypertension, and the results have been adjusted using the Bonferroni correction. You can also do the test by going through Analyze, Non-Parametric Tests, Legacy Dialogues, K independent samples, and here in the test variables you add time to first event post attack, and in the grouping variable add the BP. Define the range as 0 as minimum and 2 as maximum. Click on Continue. Choose the type of test as Kruskal-Wallis H and click OK. However, after this you have to go ahead and perform the post hoc tests, that is Mann-Whitney U test, to ascertain the pair between which the difference is significant, and also the Bonferroni correction to control type 1 error. So the former method is an easier and quicker method to do the Kruskal-Wallis H test. For the Friedman test, which is a non-parametric alternative to the two-way ANOVA, we look again at the diet study sample dataset in SPSS, and here we test the null hypothesis. The distributions of weight, first interim weight, second interim weight, third interim weight and final weight are the same. Go to Analyze, Non-Parametric Tests, Related Samples. In the objective, click on Customize Tests, go to Fields, select the weights, that is the first interim weight, second interim weight, third interim weight and final weight in your test fields. Go to Settings, choose Customize Tests and check the Friedman's two-way ANOVA by ranks K-sample with the multiple comparisons all pairwise and click on Run. The significance here is less than 0.05 and hence the decision is to reject the null hypothesis. Let us double click on the hypothesis test summary table to see the post hoc test and determine between which groups is the difference actually significant. Go to View Pairwise Comparisons. Here you see that the differences are significant between the final weight and the second interim weight, final weight and first interim weight, final weight and weight, that is the initial weight, third interim weight and first interim weight, third interim weight and initial weight. And the results have been adjusted using the Bonferroni correction for multiple tests. It is also significant for the second interim weight and the initial weight. So, these are the results from the Friedman's two-way analysis. Going on now to the non-parametric test of monotonic association between two variables, the Spearman's rank correlation test. Let us take the stroke survival dataset and check for bivariate monotonic correlation between the ordinal variables history of myocardial infarction or MI, history of ischemic stroke or IS, and history of hemorrhagic stroke or HS. To conduct the analysis in SPSS, go to Analyze, Correlate, Bivariate and move these three variables to the Variables box. Check the Spearman's correlation and uncheck the Pearson's correlation. Keep the flag significant correlations box checked and click OK. The results show that the correlation between the history of myocardial infarction and history of ischemic stroke is -416 with a significance less than 0.01, and the correlation between history of MI and history of HS is -0.423 with a significance of less than 0.01, and between history of IS and history of HS the correlation coefficient is -0.405 and significant at a level of 0.01. Also, since the absolute values of all the coefficients are greater than 0.3 but less than 0.6, we can say that it is a fair correlation as per Chan et al. 2003 for medical data. Based on your field of research, you can check the appropriate interpretation for the correlation coefficient that you get. Also note that the correlation coefficient is negative, which leads us to the conclusion that there exists a negative fair correlation between these variables. With that, we come to the end of this hands-on session on calculation and interpretation of non-parametric tests. In the last week and this week, I have demonstrated how to perform parametric and non-parametric hypothesis tests using SPSS. SPSS has many more functionalities and can be used for a host of other statistical tests. Do practice the tests that were discussed this week and last week on SPSS and explore other tests as well. If you have any questions, do raise it on the Q&A tab of this course. Also, join the Telegram group for the course using the link given in announcements. Thank you.